Okay, in this section, we talk about the meaning of deformed coordinate and undeformed coordinate. This is a very important subject. Okay, this is a very important subject. So we talk about what is the exact meaning. Let me give you some concrete example. For example, everybody knows in civil engineering, we are quite familiar with the beam model. A beam like this, simple beam. And then we have a coordinate like this here. And then we say that this one we have a point A, point A. We have a position vector. This one is the undeformed coordinate. Okay. For two-dimensional case. For three-dimensional case, we have the generalization very easily, just x1, x2, x3. But now we just confine ourselves to two-dimensional coordinate in order to make the things simple. Okay, and then the simple beam will be deformed by some loadings, right? Okay. And then this point A will go to point A prime. Okay. The point at in the undeformed configuration will be deformed into a deformed configuration. And then we have a deformed coordinate. Okay. This is the deformed coordinate. And let me give you the name. This is a deformed coordinate of point A. Okay. And this one, x equal to undeformed. Okay, the same material point from point A to point A prime. Okay, we have the coordinate x here, and then after the deformation, we have a new coordinate called the y. Of course, we have the relation y equal to y hat x1 x t, xt. So, this t means the time variable. Okay, and we can also we can also write it in this way, and more elaborate expression can be written like this. Okay. This one just equivalent to this one. Okay. This, the whole set equivalent to this handy formula. Okay. And we can also write it in terms of the initial rotation. yi equal to yi, x t I 1 from 1 to 2. Okay. And also this equal to yi x j t j 1 from 1 2 means that we have yi x1 x2 t. They are all the same. Now, if j1 from 1 to 2, okay, if I1 from 1 to 2, okay, if I equal 1, we have y1, okay. I equal 1. If I equal 1, I equal 1 here, you get y1. If we have I equal 2, and then we get y2 again. Okay, so in this formula, we can connect the deformed material point to the undeformed material point here. And y is called the deformed coordinate. X is called the undeformed coordinate. Okay, so in this way we can talk about our deformation in a more systematically way. Otherwise, the idea is not that clear. Okay, now we can talk about the displacement too. Okay, displacement vector is just the difference between y and x. Okay, in this picture, we can draw the displacement vector here. This is the displacement vector. Okay, this is y and this is x, and the difference between this is displacement vector. Okay, and let me draw a clear A prime, y, and also, of course, this is the coordinate, origin of the coordinate, and then u, okay, in a more clear way, okay, because we have some expression here to cover the line, so we draw the picture here such that you can see it clearly. Okay, in the same way, we can express our what? Okay. But I want to remind you that such kind of rotation have some trouble if we talk about large deformations. But at this stage, because we are just at the very beginning, so I don't want to confuse you too much. So we just take it for granted. In a later part of this course, we should beware about the difference between y and x, and then the index may not be expressed in the same way. But at this point, we just take it for granted. And then we have, with this functional relation, we can have also this. Okay, I think it is clear enough. So this is the material point coordinate, undeformed coordinate, and also I want to remind you one thing, huh? Okay, it means that we have a relation between y and x. And we also have the relation like this. Okay, and then for more convenient expression, we express it just like this: dy yes, this is the total differentiation, huh? Total differentiation of y. But if we drops out the dependency of dt, drops it out, cancel. And then for a fixed time, for every fixed time, moment of time. For every fixed moment of time, we have dy equal partial y partial x dx. Okay, I want to introduce you a new relation now. See here, a undeformed coordinate of a point can send you to a deformed coordinate of the same point, okay? Point. Coordinate of a point, okay? Also this is coordinate for a point. But now, here, this is differential of the coordinate. It means that it is the material line. It is not a point anymore. It is a line. Material, line of material, material line. Okay? And this one is also a material line. But it is in the undeformed configuration. This is the undeformed material line. This material line, of course, is a deformed material line. Okay, so we have the relation here, and then take the differentiation and fix the time, and we get the relation between a undeformed material and a deformed material. This is a very important relation we have, because if you want to talk about the deformation of a body, you must get all the information about every material and also the deformation of the material. So this is the relation you want to have. Okay, you have a material line in an undeformed coordinate, and then you send this material line to the deformed coordinate. Okay, let me show you a more detail about this concept. We have a beam here, simple support beam, and then deform. Deformation. Okay, and then you bend down like this. We draw it in an exactly manner, and then we say that we have a point A, and then we have another point called B. Okay, B. Not necessary in a horizontal way. So we have a point A, X, A. You have another one, X, B. Okay, another point we have a coordinate. This point we have coordinate, another point we have a coordinate. Of course, we have two components, and also this one. See here, connecting these 2 points, we have a material line. Okay, this is the material line. Okay, undeformed material line. Okay, so this one is and then after the deformation, where these 2 points go, maybe they will go to here, A prime. A go to A prime, B go to B prime, maybe. Okay, and then connecting these 2 points, we have another material line called the dy here. Okay, this is a typical deformation of a material line. Of course, there are infinitely many material lines around here. So we have infinitely many deformed material lines too. So of course we have in the same way we have YA, YB like this. Okay, and then YA, and then YB are a lot of not very beautiful, but you understand what I mean. It is a straight arrow, but I just draw it in a very ugly way. Just forgive me. Okay, so something like this. Okay, so in this way, we send a material line from here to here. A material line, AB here. Finally, it becomes here. A prime, B prime. This is dy. And this is dx. Okay, deformation. Understand? Okay, after the deformation, this material line will become like that. Okay, the length maybe become longer, and also the direction is different now. Okay, they have different directions. Okay, so you want to ask, what is the relation between dy and dx? What is the relation between dy and dx? This is the key relation we want to have for the analysis of the material, because if you have this relation, you have the strain and you also have the stress later. Okay, and I tell you what is the relation here. The relation here is this one. So this relation is a very important relation, and where this relation come from? This is the most original relation we have. We have the correspondence between every material point. We have every x here and get another y, and another x get another y, xa get ya, xb get yb, xc get yc, such and such. A lot of material points here, and then they will be deformed. And also from here, we will have this mathematical relations. And then from here, we get the mechanical interpretation that this one is the undeformed material line, and this one is the deformed material line. The picture is like that. Okay. So far, maybe you will feel that the thing I talk about is too abstract for you. Okay. So I think I need to give you a concrete example to show what this how this formula can be worked out. We have an example. Okay. Given x1, y1 equal to x1 squared plus x2 y2 equal to x1 x2 plus 1. Is it appropriate? I think maybe. Okay. Plus x1, yes. Given this, okay. So basically, this one can be written as for a certain moment of time. So for a certain moment of time. So in this formula, you don't see the time variable. If you want to consider the time dependency, we can add in, no problem. Okay, but at this stage, we just look at the simple problem without considering the time variable. Okay, here we get the mathematical expression of y1 and y2 in terms of x1 and x2. So we have y. So let me do the differentiation here for you. Okay, this is the differentiation we want to have, and this is the material line, and this is the material line too. This is the undeformed material line. This is the deformed material line. Okay, and then what it is, let me show you. dy1, dy2, the partial y1, partial x1, partial y2, partial x2, partial 2y2 partial x1 partial y2 partial x2 dy1 dy2. Okay, and then this one can also be expressed as dy equal to partial yi partial xj dxj. Okay, like this. This one equivalent to this one, and this one equivalent to this one. When we put I equal to 1, we get dy1. And I equal to 2, we get dy2. Okay? And then this is y equal to I equal 1, xj equal to x1, such and such. And also, let me do some correction here. This dx1. And also, we want to have a more elaborate weight. Okay, this dy I equal to partial yi partial xj dxj equal to summation j equal to 1 to 3. This is a notation called the Einstein notation. What is the Einstein notation? Einstein notation is this. When the index is repeating itself, okay, we have j and j here, means that we sum it over 1 to 2 or 1 to 3, depending on the range. Okay, and you can omit this one to get here. Okay, but they are equal. If you see here, j is repeating, and then you sum it over. Okay, so in this way we have why? Because this is a summation from j equal 1 to j equal 2. J equal 1, we get this point. And j equal 2, we got this point. Okay? And we get and then we sum these two terms up to get this one. I. Okay? This j repeating itself, and then we sum it over to get the yi for I equal to 1 and 2. And now I equal to 1, we have the y1 equal to partial y1 partial x1 dx1 partial y1 partial x2 dx2, because I equal to 1, 1, 1, we get 1, 1, 1. And I equal to 2, we have dy2 equal to partial y2 x1 dx1 partial y2 x2 dx2. See, I equal to 2, 2, 2, 2, 2, 2, 2. Okay, 1, 1, 1, 1, 2, 2, 2, 2. Okay, and this one can be expressed in terms of a matrix, because you see here, if you multiply this row to this column, this term times this term, we get this one. This term times this term, we get this one, right? So this is a perfect way to write it in terms of a matrix. Okay, and also for here, dy2 equal to this term times this term, this term times this term, and sum it up. This term times this term give you this term. This term times this term give you this term. Okay, so this is just a matrix. Okay, this one, this one, this one, this one, this one. Okay, and also these two. In this way, we can construct the relation between the x vector and the y vector. Remember, always remember, this is the material line. Material line, undeformed. This whole vector, the whole vector represents an undeformed material line. This whole vector represents the deformed material line. Okay, and now we can put our function relation here to calculate this matrix. Okay, let me show you the point here. Let's continue. Okay, dy1. What is dy1? Y1 here is x1 squared plus x2. x1 squared plus x2. Okay, we put this expression into this differentiation. And then here, we perform the differentiation with respect to x1. So this x2 drops out because x1 and x2 are independent to each other. So the result of this differentiation will be only 2x1. Understand? We differentiate x1 squared plus x2 with respect to x1. And then this one doesn't give you any result, and this one gives you 2x1. In the same way, we put this expression into here. This is x1, x2 plus x1. And then we, at this time, we differentiate with respect to x2. So this one differentiate with x2 will give you x1. And this one differentiate with respect to x2 gives you 0 because x1 and x2 are independent to each other. Okay, so as a result, this one gives you 0, this one gives you x1. Okay, and also we can do the same thing. Okay, I made a serious mistake because according to okay, I must do some correction here. This is y1, so this one should be y1. So this one shouldn't be like this. We should put still x1 squared plus x2. See why this is y1? See here. Yes. This one comes from the relation. Okay, this is the y1. So I made some mistake before, but now I do the correction. y1. Okay, consistent. So since this is y1, we should use this function y1 x1 squared plus x2. So with respect to x2, so this one will drop out because x1, x2 are independent. So this one differentiate with respect to x2 equal 1. Okay. Now y2 equal to x1, x2 plus x1. Differentiate with respect to x1, you get x2 plus 1. And then this one, again, x1, x2 plus x1. Differentiate with respect to x2, you get 0 here, and again you get x1. Okay. Now we get the relation between dx and dy vector. Okay, in this concrete example, I show you how to calculate their relation. See, in different points, we will have different relation between dx and dy. For example, point 1, point D, point E, okay, point E, okay, point E, x1, x2 equal to, for example, 2, 1, 2, 3. They are located at the coordinate x1, x2, 2, 3. Okay, and then at this point, what will be the relation between the deformed material and the undeformed material? Two x1. Now x1 is 2, so you have 2 times 2 plus 1. X2 is 3. 3 plus 1, and then 2 plus 2, and then this, it is 1, and then this x2 is 3 plus 1, and then x1 is 2. Yes. Okay. Two times 2. Okay, this is 2x1. This is x2 plus 1. This is x1. This is 1. Okay, and then since x1 is equal to 2, we have 2 times 2. So this x2 plus 1, x2 equal 3. So 3 plus 1. So as a result, we have 4, 1, 4, 2. Yes, dx1, dx2. Okay, this is the concrete relation between the undeformed material line and a deformed material line. Okay, and also if you have a picture like this, point, we have another point. Point E, point D, okay, another point, x1, x2 equal to 4, 1. And then, in the same way, you can get the relation between the undeformed material line and the deformed material line. Okay, for example, x1 equal to 4, so this 8, and equal 1. x2 equal to what? 1, so 1 plus 2. x1 equal to 4. Let me check it twice, see whether I make any mistake. Correct? x2 equal 1, yes, correct. x1 equal 4, correct, yes. And so as a result, at point E, we have this relation. At point D, we have this relation. So at different material point, you can imagine the deformation will be different, okay? For example, we have a beam, a very thick beam, very, very thick, very, very thick. For 1, yes. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. So what is point E? Point E is 2, 3. Yes. This is point E. Yes, this is point E. Huh? We have a beam. Huh? Actually, we are talking about a material point in a beam. And what will be the point D for 1? Here, 1, 2, 3, 4, 1. This is point D. Understand? And then what will be the material? What will be the relation between the material line around point D and point E? These two are the relation between the material, the deformation of the. These two will give you the deformation of the material line around point D and point E. Deformation, deformed like this. Okay, and see here. We haven't talked about what is dx1, dx2. Huh? dx1, maybe this is dx1. Okay, vector, and not dx1. This is dx, and which can be decomposed into two components. Okay, dx1, dx2. We have a vector. You have a component expression, and maybe the material point, the material line expressed in this way, and you have the dx1, dx2. Okay, and you may have another material line dx. You have also the vector, a lot of dx. Every dx will be sent into dy according to this matrix relation. And this is the relation around point D. Okay? Around point D, the material line will be deformed into another material line according to this matrix. Okay? Point D. How about point E? Point E, again, we have a lot of material line. How they deform? They will be deformed according to the formula. This point E. Huh? All these material line will be deformed into another material lines according to this matrix. Okay? So the matrix relation will give you the precise direction and the length of the material lines after the deformations. Okay? This is a concrete example to tell you how this relation between material line can work out. Okay? Okay, in different material point, we will have different deformations. Okay, point D and point E will be deformed in different way. Okay, so of course they have different matrix relations. Now let me tell you how this work out in more detail. How this material line go to? Okay, where they go? For 1, okay? In order to point E, okay. Two, three, yeah, point E. In order to get a more precise picture of this deformation, so we forget point D at this time. Okay, yeah, let us have a clear picture to illustrate this idea. So we don't draw the material line around point D. Okay, see this is point E. Okay, point E. The material line will be deformed in this way. Okay. Okay. Now we consider one material line. This one. Okay. This one we give you a name called what? ABC 1, 2, 3. No. 甲乙丙. Yes, because we are talking about this, we are teaching this class in Taiwan, so we use some Taiwanese characters or Chinese characters. Okay, you understand what I'm talking about. 甲, okay, dx 甲 means A. ABC 甲乙丙, okay, dx 甲. And also we have another material line too. dx 丙. Okay, different material line. We have also another material line, 甲乙丙丁甲乙哈. Okay, we have different material line. First one, second one, third one. Of course, we have different right here. I just don't want to write it out all. Okay, so different material line will be deformed into different material lines. Okay, how about dx 甲? Let me see. I use a delta. Delta means that a very small, infinitesimal term. Because this is an infinitesimal material line, so I use a delta here to represent a very, very small term, 10 to 0. Okay? And the direction is horizontal. 1, 0, okay, horizontal. E is times the very small material line, x. This one, 1 square half, 1 square 2, 1 over square 2 is this one. And this one here. Okay. With this material line, we can send it to another material line by this matrix relation. Here, 4, 1, 4, 2. here 1, 0. So the result is 4, 1, 4. And this 4, 4. Yes. See, this material line will send to a horizontal, not horizontal, in a 45-degree direction. Okay, let me tell you the result. After the deformation, point E dx 甲 will send to, a point at 45 degrees, because 4, 4 means that 45 degrees, okay? Like this, understand? And how about dxE? Another material line, dye will come from dxe. Okay, and what will be the dye dxe equal to 1 over. Okay, and then we calculate the result. According to this matrix, 4, 1, 4, 2. See, before we used this matrix also. Okay, and now we have. Okay, what will be the result? Let me tell you. 4, 1. So the result is 5 over square 2. 4, 2. 6 square 2. So, where the material line go? Okay, this is the material line drawn according to this vector, and this material line 5, 6, so a little bit higher, like this. Understand? In this way, step by step, we can construct the relation between the undeformed material line and the deformed material line, point by point, line by line. Okay, point D, point E, point F, point G, a lot of points, and around different points we have different material lines. Okay, see, we have point E here. Of course, we have point D here. We can have point A here, point B here. Okay, they will send all this. They will be sent to different material line. Okay, according to this matrix. Okay, I think this is the complete picture I want to show you. Okay, I hope you can understand what I talk about. If you don't understand, please ask me in the class.